Hello and welcome to this course. I am Dr. Sriram Kumar. Today we are going to learn physical vapor deposition technique. Let's understand what is this thin film deposition technique first, and then we will start physical vapor deposition technique. So if you are looking for some particular techniques for your thin film deposition, so we have a different options. Maybe you can use thermal evaporation technique, maybe the sputtering technique, or maybe electron beam evaporation technique. So these three techniques are PVD, that is the physical vapor deposition technique. Maybe you can use chemical vapor deposition technique, that is CVD technique. So PVD technique and CVD techniques are the most popular kind of the technique in thin film deposition. Apart from these two famous technique, we can also use spin coating techniques. We can use deep coating technique. Maybe we can use molecular beam epitaxy, or maybe slot die coating. So these are the some common use thin film deposition technique. And you might thinking about the application of the thin film. So thin film has diverse application areas. It can be used in this photovoltaic and the electronics application. Even though these thin film deposition techniques can be used in this medical devices, so you can passivate the medical devices to prevent some kind of corrosion or the contamination. So for that, we need to use the thin film depositions on the medical devices. We can also use that thin film deposition in the fabrication of the lithium and batteries. We can use that thin film maybe in the superconducting PVD kind of techniques in this quantum application. Maybe we can use in some magnetic thin films, organic electronics. So these are some important areas of research where you can use thin film for diverse applications. Now let's understand what is physical vapor deposition technique. Physical vapor deposition technique is techniques so that we can use to deposit thin film. And using the PVD technique, you can deposit the material from 2 to 5 micrometer thickness on any kind of the substrate. So using PVD technique, you can have the thickness of the material on any substrate from 2 to 5 micrometer. So now let's understand how physical vapor deposition works. So in physical vapor deposition, we have the closed chamber in which we have the substrate here. So you can place your substrate. Maybe your substrate, maybe do a single substrate, or maybe there's multiple substrate in that chamber. And you have here your target material. So the position of the target material is maybe the one or maybe the multiple target materials. So in particular case, if you have this one, two, and the three target materials, and this deposition techniques works under this very high vacuum. So here the vacuum is from 10 to the power minus 4 to 10 to the power minus 6 door pressure. So it works at extremely very low pressure. So you need to pull down all these pressures to in this particular pressure range, and then after we can use the such kind of the neutral gas. Here the neutral gas we can use is this argon gas. And once you have this kind of the setup, then after we need to evaporate our desired target. So here we have a target, and we need to make that bulk material into the vapor phase. And once that becomes in the vapor phase, you have the here the uniform vapor surrounds around this your substrate material, and that vapor gets deposited on your substrate. So here the evaporation, so you had you had this bulk material, and you want to make that bulk material into the vapor phase. So here there are the different techniques. So we can use that techniques to make that bulk material into the vapor phase, and that vapor phase of that material gets deposited on the substrate. Suppose you want to deposit gold nanoparticle and maybe the gold thin layer on silicon wafer. So for that we need to use here this either gold plate or gold wire, and we can make into the vapor phase by the either thermal method or maybe the electron beam method, and based on that have we can we will have the deposition of that gold nanomaterial on that substrate. Now let's understand. So based on the different kinds of those technique, we have the different physical vapor deposition method. So here we need to have vapor form of that material. So we need from the solid material, solid to vapor phase, of the material. So here these techniques can be used to convert that use solid material into the vapor phase. So first technique is the thermal evaporation. So by heating that use solid material, for example, if you have the gold, material, and if you want to make it the vapor of the gold, so either we can thermally heat that material into the vapor phase. Second is the electron beam evaporation technique. Third is the reactive activators reactive electron beam evaporation technique. Fourth is a sputtering technique. Next is filtered cathodic arc deposition technique, and splitting and the pulse laser deposition technique. So in this class, we are going to learn thermal evaporation techniques. We are going to learn about the electron beam evaporation technique. We are going to learn about a sputtering technique and the pulse laser deposition technique. So we are going to learn these four techniques. Let's understand first technique, that is thermal evaporation based technique. So in particular technique, we have this closed chamber, and here we have our desired target material. Suppose here this is the gold material. So that gold material may be either in the crucible or maybe as is this gold material on the solder. And somehow we can heat this material by the heater here, so that this solid material becomes in the vapor phase, and that vapor phase gets deposited on the silicon wafer or the desired substrate material. Based on the kind of the heater, we will have a different kind of the thermal evaporation technique as well. So let's understand what are the different kinds of thermal evaporation technique. So we can convert solid material into the vapor phase, either we can use the direct resistive heating. In the second case, indirect resistive heating. Third is the either we can use the inductive heating, and the fourth one is the laser ablation or the laser evaporation technique. So we can use four different kind of the heating methods to make the solid material into the vapor phase, and based on that, that vapor phase of material gets deposited on the substrate. So now let's understand what are these kind of the heating methods. So in the direct resistive heating material, so here we can have that material either suppose we want to convert that gold solid material into the vapor phase, right? So what we can use here? So either we can use the wire of this gold. So maybe we can use the thin wire of the gold, or maybe we can make this coil of that wire. So here, so either we can use it in this form or maybe in the wire form, and we can apply very high voltage in these two terminals. So if we apply very high voltage in these terminals, what happens? So that material gets evaporated, and we will get that vapor phase, and that is deposited on the substrate. So in direct resistive material, we just apply the direct high potential between these two terminals, either in the wire form or maybe in the coil form. So in this kind of the technique, we can use these kind of the materials to deposit on wafer substrate. Maybe we can chromium, iron, molybdenum, nickel, palladium. So this kind of the material we can use to deposit on the substrate. We have the other kind of the heating, that is the indirect resistive heating material. So in this kind of a technique, so here we have such kind of this container that is called the crucible. So we put our material, so that material maybe the in powder form, or maybe in the crystals form. So we can put this material in this crucible, and we apply the heating in surrounding of this crucible, so that that material gets in the vapor phase from the solid phase, and these are the vapor phase, and that gets deposited on our the substrate material. So here we are not directly heating the material, but indirectly we are heating in their surroundings, so that that materials get deposited. We have the third kind of the deposition technique, and that is the inductive heating. So in this particular techniques, we have this coil. So in between this coil, we can put our the desired target. So this is the target material. And if we put the target material in this coil, and if we apply the very high current in the terminal of this coil, what will happen because of inductive heating? So that is the localized heating in that target material, and this target material is from the solid state material, so that becomes the vapor phase. And again, we can use that vapor to deposit the material on the substrate. And next important kind of the thermal evaporation technique is kind of the laser ablation, or the laser evaporation kind of a technique. So in this particular kind of a technique, we have here target material. So this is our target material. And when we put the laser, high power laser on this material, so we have the target material, and we put the laser there. So there is the localized heating on the target material, and based on that the atoms or the plasma from the target materials comes out. So we have the kind of the plasma here, and this plasma gets deposited on the substrate. So in this particular kind of the techniques, we are using lasers to form our solid material into the vapor phase, and based on that, we will have technique that is called the laser ablation or the laser evaporation technique. So in the thermal evaporation, we understand there are the four kind of techniques that can be used to make solid material into the vapor phase. Now just understand what is the significance of vacuum in the CVD technique. So we have this container, closed container, or the chamber in the PVD technique. So in PVD techniques, we need to make very, very low pressure. So here we will have the 10 to the power that 4 to 10 to the power minus 6 toward pressure. Um, so we are going to use very, very low pressures. So here we will make these pressures in these two stages. So first stage is from the atmospheric pressures to, so let's understand from 1 to 10 to the minus 3 to a pressure. We can make, or maybe we can from 760 to pressures. So either we can have make low pressures by using initial low pressure by this mechanical pump. So we are going to use mechanical pump. So initially we will use the mechanical pump, and the second stage from 10 to the power minus 3 to 10 to the power minus 6 to pressure, we need to use the very high vacuum pump. High vacuum pump. So we need to use this two kind of the pump. Now you are thinking about, okay, why don't we can use the high vacuum pump from atmospheric pressure to the 10 to the power 6? But problem is that very high vacuum pump cannot be used from high pressure. That can only use from at low pressures to the extreme low pressure. So here we can use two kind of the pump. One is the mechanical pump, and the second is the high vacuum pump. In this two stages, the one and the two stages. And then after we can achieve that extreme low pressure in the PVD technique. Now let's understand what is the consequences or the effect of this very low pressure on deposition of the nanomaterials or the thin film. Here we have mean free path. So this mean free path depends on the pressure of that vapor in the chamber. So suppose the temperature of the chamber is fixed, and the dimension of that gas molecules is the fixed. So if we have the temperature is fixed, and we are using the same kind of the gaseous molecules, so in this case these are fixed, but we have only dependency on pressure. So here if we have pressure is very high, that means here we have the lambda is very, very low. And here the lambda is the mean free path. Suppose you have this gaseous molecule of the atom. So, so it moves before colliding with the, so suppose this is A and this is the B. So you have the one molecule here, and that is colliding with the molecule B. So before colliding molecule B, the average distance traveled from point A to point B before colliding to B is called the mean free path. And if we have here very high pressure, that means there is very, very less mean free path. But if you have the very low pressure, in that case, you have very high mean free path. So that means you have the chamber and you are putting your vapor, you are putting vapor phase of that solid material in the chamber. So in that case, there is very less probability of colliding the molecules together, and that will improve the overall this deposition of the material on the substrate. So now let's understand with the example how the pressure change the mean free path. So suppose if the size of the gaseous molecule is 3 angstrom, and we are depositing at the 300 Kelvin temperature. So, so based on that, we can have the simplified version of the mean free path. So here that is something constant divided by the P pressure in the door. So suppose if we have the very low pressure, that is 10 to the minus 6 door pressure. So in that case, here lambda is close to the 78 meter. That is huge. That means that gaseous molecule will travel close to the 78 meter before colliding with the other gaseous molecule. And that is huge. And that's why you have the substrate here. Maybe you have the substrate, you have the closed chamber, and you have put the substrate there, and you have the target material there, and you are hitting this one, applying the maybe the high voltage. So because of the very high mean free path that can travel from here to there, that can travel from here to there, and that vapor gets deposited on that different substrate. So here you have substrate, and here you have target material. So this so that can travel easily and gets deposited on the substrate. So this is the importance of the pressure in deposition chamber. Now let's understand what is the kinetics of the depositions and how the kinetics gets affected at a different angle. So now let's consider one case where we have point source. We have the one point source, and you have suppose this kind of semi-R kind of the system where you have the different kind of the materials. Suppose you have the different kind of the materials. So here, this point source, from this point source, that vapors travels from here to different angle, right? So that will go maybe 1, 2, 3, 4. So if that will gets deposited on 2, maybe 3 and 4, so then will different angle based on the support. So this is the vertical, and if that move from here to there, so that means there is that's theta values that need to travel from here, that vertical point to the that fourth sample, and based on that you will have gets affected, so you will get the different kind of the kinetics of the deposition as compared to two at four substrate. And at the same time, you have also the different radial distance. One is the theta values, and one is the from suppose you have the r here, and you suppose and based on that, and we have the also this distance from here from here to there. If suppose this is in a semi in circular path, in that case we have the same values, but if we have the just same arc values, so in or maybe the same semi flat kind of things, so in that case you will have the also dependency on these r values. So in the case of the point source, you have the two parameters on which that deposition affects. One is the r values and one is the theta values. So in the case of the point source, the flux of that vapor on that particular substrate depends on the cos theta. So that is cos theta, and here is the radial distance from here to there. And here R is the rate of evaporations from that point source. And if you have such kind of planar source material or planar target material, so you have the planar target material, and you have different kind of the different, you have substrate at different place. So in that case you have such kind of depositions. So maybe the vapor comes from here or maybe here. So in that case you will have the dependency on these two parameters. What that parameters is about, one is the theta. So if you have the two theta values, if this is the theta I, so one is the this theta I, and once at the vertical point, so you will have the different kind of the theta k. So you have theta k and the radial distance. So in that case, you have the three variables parameters. One is theta k, theta I, and the radial distance. So we have the many variables if we have the either point source, even though in the point source, if we have the sample or the target at the different places, in that case there is the different kinetics of growth, thin film growth. And if in the second case, if we have the planar substrate, so even in the planar substrate there is the variability comes if we have the different theta k, different theta I, and the r values. So now let's understand what is the effect of theta on the this deposition of this material. Suppose this is our silicon and this is this SiO2 layer, and we want to make such kind of the devices. So in the particular case, we need to protect this SiO2 layer. So for that, we need to deposit with other kind of the materials. So we have this planar structures, and then on that planar structure, the vapor is coming through the some particular angle. So if you see here the vertical angle, so we are getting the vapor on the substrate with the some theta angle. So if that theta affects the deposition, let's understand. So here, if you see the thickness of the material, you see the thickness of the material. However, you will see the here different thickness of the material, and here you have the different thickness of the material. So it's because of the different angle of that vapor that comes. So there is a different flux of that materials coming onto this kind of the surface, or maybe and this kind of the surface. So we can improve this kind of this coating if we get the angle instead vapor at particular angle. So we can, so suppose the vapor is coming from this angle, and they, so because of that, maybe we will get the such kind of those shadowing kind of things happens, because there is no such kind of the deposition at that surface. So a vapor is coming here this way, so there is the shadowing process here. So for that, we can, what we can do is we can just rotate that sample or the substrate with 180 degree. So what happens if we just rotate from this to this direction? So in that case, there may be the deposition of the material and that surface. But but in that case, maybe we get the another challenges. In that challenges is that we will get here is the very thick kind of deposition. There is very thick kind of depositions, and we get here the very less. I mean that is not homogeneous kind of the deposition at this particular mm, site. It's because of the shadowing of this area by the upper areas. So we can improve this kind of deficiency in the deposition by maybe the heating of this wafer material. But the problem is that if we hit that wafer substrate, in that case, there may be some kind of the side chemical reactions may happen, and that will affect the overall deposition of this material. So that is this problem in the physical vapor deposition technique. So using physical vapor deposition technique, we can deposit, for example, if you want to deposit SNO2 semiconductor kind of the material, you can control the morphology, you can control how you want to deposit your material. So either you can deposit here either nano wire kind of the material, or maybe nano rod kind of the material. So this is nano rod kind of the materials, and if you add these others, nano wire kind of the materials. So you can control the morphology of the materials with the temperature control, gas control process. So based on that, you can control the overall the morphology, and based on that, you can control the overall this sensitivity of the sensor developed by based on the SNO2 kind of the materials. So till now, we understand using the thermal evaporation technique, we can deposit desired target material onto the substrate material. So we have another kind of the important technique, that is the electron beam evaporation technique. So in electron beam evaporation technique, we have a similar deposition chamber here, and we have this sample holder, and here we have this such kind of the crucible. So this is sample of the crucible, and we put the some kind of the sample. So in this particular technique, we are using electron beam as external source. So we have the electron beam here. So using the electron beam, we can just put that electron beam on the target material. So what happens? There is the formation of plasma. Evaporation happens. So if you will get the evaporation of that materials, if the electron high energy beam of the electron collides on this material, so we get the this kind. So this is the vapor of this desired target material, and this one gets deposited on the substrate. So here there is the difference is about how you are making vapor phase of your target materials. as compared to the thermal techniques. And we have the another kind of the important technique is the pulse laser deposition technique. So in pulse laser deposition technique is popularly known as PLD technique. So using the PLD technique, we can convert the target material using this laser on the target material into the plasma, and that this plasma gets deposited on the substrate. So here, PVD technique. So we till now we understand different kind of the PLD technique, and there is difference in the PLD technique based on the methods we use to make target material into the vapor phase. Maybe from the thermal technique, we can use the electron beam technique. We can use the laser technique. So these are the techniques we can use in the PLD, and we can get the good thin coating of the material from 2 to 5 micrometer thickness. And these are the YouTube uh, video link, so in which it is very good animation of the PLD technique. So if you have time, then you will go there and watch the animation, and that is very well explained in so that is close to the 3 minute video, so you can watch that short animation. And in this in second video, so it is the 8 or 9 minute in which they have explained the instrumentation of field techniques. So see you uh, in next class. In next class, we will have discussion on sputtering technique, and a sputtering technique is one kind of the PVD technique, and that is very well known technique uh, to deposit the thin film on the any kind of the substrate kind of material. So see you in the next class.